Good morning. We don't usually think of the Arctic when we're considering mid-latitude droughts and heat waves, but in collaboration with my co-authors, Fuyo Wang and Jennifer Francis, I'm going to try to convince you that maybe that is warranted. The first part of the argument should be an easy sell, and that is this familiar pattern that climate models have produced of future drying and associated heating of continental interiors. This is a result that's seen in the older CMIP-3 models, as shown at the top, as well as some newer results from Eric Maloney et al. From the CMIP-5 collection, which indicates in the interior of the continent here, we see that 2/3 or more of the 15 models indicate summertime drying, and that pattern extends to the Pacific Northwest. Now, this is a feature that has been noticed for quite a while, even before CMIP-3. Rowell and Jones came up with a nice summary describing the popular hypotheses that have been put forth to explain this pattern. The first one was enhanced land-sea temperature contrast leading to a reduced relative humidity over the land, which leads to reduced precipitation over the continent. The other favored mechanism is depleted local soil moisture during the springtime, which leads to subsequent reductions in summertime soil moisture and therefore reduced rainfall as well. A third explanation, which they downplayed, was remote teleconnections from the tropics, and that would lead eventually to less rainfall over the continents. Now, what I'm going to argue is that perhaps that there is something to a teleconnection, but from high latitudes rather than low latitudes. And this idea is not entirely new. In fact, 10 years ago, Jake Sewell and Lisa Sloan described a climate model simulation in which they found wintertime drying across the northwestern U.S., West Coast, I should say, and they attributed that to a decrease in Arctic sea ice, which led to inflated geopotential heights locally in the Arctic, and then somehow those height anomalies migrated into the North Pacific, built up a ridge, and explained the reduction in rainfall there. But it wasn't clear what the physical mechanism would be to move the pressure anomaly from the Arctic to mid-latitudes. In a paper a couple years ago with Jennifer Francis, we put forth a physical explanation for how the Arctic might be affecting mid-latitudes dynamically in terms of extreme weather. That is that Arctic amplification of global warming causes a slower and a more meandering circulation pattern, as shown schematically in this slide. So the idea is that as the Arctic warms faster than mid-latitudes, that would lead to two consequent effects. One was a stretching of waves meridionally, higher amplitude Rossby waves in general, as well as the slowing of the circulation as you get a reduction of the mean westerlies. And that paper didn't really give evidence for future support of the hypothesis, but we have since done that. And this is an example from the CCSM-4 climate model, which I'll be describing the rest of the talk. This is the model's change in 500 hectopascal zonal wind during the summer by the late 21st century. And you notice the main pattern here, the most interesting pattern, is that you get this weakening of the westerlies, shown in blue, throughout the hemisphere. It's a contiguous pattern, and it's particularly pronounced over the United States. And you see the bullseye over the west central United States, which is relevant for this talk, because that's a favorable pattern for drying and enhanced heating. So this was sort of interesting to us, and it provides motivation for today's study. We'll be using the CCSM-4 climate model the rest of the talk, driven by the high-end RCP 8.5 greenhouse forcing. All the results will be from the late 21st century compared to the late 20th century, and primarily during summertime. And for robustness, we looked at 5 ensemble members, and I'll be describing those 5, but mostly the ensemble mean. The CCSM-4's pattern of precipitation change during the summer by late 21st century is very similar to that of the CMIP-5 collection. You see this pattern of general drying in most places, but it's particularly pronounced here in the central part of the continent, up to a 30% decrease in summertime precipitation, and like the CMIP-5, that drying pattern extends to the Pacific Northwest. Interestingly, there's an increase in precipitation along the east coast of the United States. And that pattern in the ensemble mean is very similar among the ensemble members, regardless of which ensemble member you pick, they show qualitatively and quantitatively the same basic pattern, that you get this pronounced drying in the interior and that it extends northwestward to the Pacific coast. And not surprisingly, as in the same places where we get this enhanced drying during the summer, there's also strong summertime heating at the surface. And this is the ensemble mean pattern, which is showing up to a 7-degree warming by late century during the summer, largely in this region of reduced precipitation, and again extending to the northwest coast. And like with precipitation, we see the very similar patterns spatially in the surface temperature changes throughout all 5 ensemble members. The proximal cause of this enhanced drying and heating is the change toward a more ridge-like circulation pattern, as shown here. This is the change in the summertime 500 hectopascal winds in the ensemble mean. You see this general ridging pattern along the U.S.-Canadian border, which has a core in the northwest part, but it really is draped across the entire border and extends over this whole region. And so when you get this pattern developing, for whatever reason, it favors this drier, warmer, outflowing air, subsiding air, and very consistent with the sort of pattern synoptically we see during extreme dry conditions and hot conditions in the central U.S. What's interesting is that this ridging pattern over the U.S. of North America is not in isolation. We find that it actually extends hemispherically, as shown by this shading of 95-meter height increases. So taking a step back, this is the late 21st century pattern of geopotential height changes during the summer. You see increases everywhere, which is indicative of the warmer climate in the higher greenhouse world, but the height increases are not the same everywhere. So the biggest increases are occurring here in mid and high latitudes, as shown in the shading. And the other feature of note is the local minimum in the very highest latitudes around Greenland and the archipelago, which could be thought of in a relative sense as troughing. So these are the 2 key features that we identify. And what's of note is that this ridging band is not symmetric about the North Pole. If I put on this 60-degree north latitude band as an overlay, you can kind of eyeball that in Eurasia, the band tends to be north of 60, whereas in North America, it's distinctly south of 60. And you can see that a little more clearly when I put arrows around the core of this ridging band. You can see that throughout Eurasia, that the core of the ridging band is located in northern Siberia, north of 60, and then over North America, it's located farther south with a peak in North America around the U.S.-Canadian border. And that's important, of course, because it's the location of this ridging pattern in North America that gives you the favorable outflow of warm subsiding air that promotes the drying and the enhanced heating of the continent. Similarly to the other variables, we find a lot of resemblance in the ensemble mean and the ensemble members pattern compared to the ensemble mean. In every one of the 5 ensemble members, we see the same pattern, that the core of the ridging is farther north in Eurasia, farther south in North America. It's more pronounced in certain ensemble members than others, but it occurs in every one of them.